Welcome everybody. We are pleased to have as our guest Eiichiro Komatsu, who has recently become a new director at the Max Planck Institute for Astrophysics in Garching. And so we're very happy that he has accepted to come to us and tell us about his work. Let me give a very brief curriculum vitae. He has done his Bachelor of Science degree and his Master's degree at the end of the 90s. 1999, his Master's degree at the Tohoku University, I hope I pronounced it right, on the topic of cosmic microwave radiation, and also appendices on gauge invariant general relativistic perturbation theory and light propagation. Then he obtained his PhD in 2001, also at Tohoku University, on the pursuit of non-Gaussian fluctuations in the cosmic microwave background. He has then moved to various places, also to Texas, Austin, becoming an assistant professor and associate professor at the University of Texas in Austin, and became a director of the Texas Cosmology Center, also in Austin. And recently, he then in 2012 moved here to Germany to take up his directorship at the MPA and also be a professor at the Ludwig Maximilian University. He received various awards and prizes, among them the Gruber Cosmology Prize in 2012 and the Sophie Tycho Brahe Visiting Professor in the University of Copenhagen and the Nishinomiya Yukawa Memorial Prize in 2010. And I can go on because there are a number of them. But I would like not to steal much more time from him. So let us welcome him here to Heidelberg, and I'm looking forward to your talk.
Thank you very much. Thank you very much for kind introduction. It's a pleasure to be here. I think the last time I was in Heidelberg was 3 years ago almost, when I was in town for a job interview for Max Planck job in NPIK. That was a very stressful visit. And this time I have a much more relaxing visit, so I'm very pleased to be back here for such a relaxing environment. As Professor Dermond said, I spent a fair amount of time thinking about cosmic microwave background. That was my master's thesis topic, PhD topic. I'll be working on this forever. And it's almost coming to an almost end, perhaps 5 to 10 more years, and hopefully we'll move on to some other things. But this is sort of so cosmic microwave background can do many things, but my primary interest has been to really nail the theory of the early universe using cosmic microwave background, and we have made a tremendous progress over the past years on this topic, and I hope I can give you a summary of what we know and what we're going over the next 10 years or so. So just a reminder, so we are doing cosmology, and what we're doing is to figure out the old questions like the age of the universe, the size of the universe, if it is actually finite, what kind of shape, the constituent, and then how did it begin. And my talk will be solely focused on this part, although I do touch on this as well, just a little bit. And of course these are interesting questions, but for a long time this wasn't considered as science because cosmology was often said to be a subject for retired professors. No longer the case, I hope, because of this breakthrough that you can really observe this, right? So essentially what we are doing using cosmic microwave background is to take advantage of the fact that if you look at distant objects, you look at the past, and if you just make an effort and keep looking at distant objects forever, you eventually see the beginning of the universe. That's all. That's all we do. So this cosmic micro background is the first light of the Big Bang, and let me show you how that works. So I'm going to show you this movie from DVD called Cosmic Voyage. It's a very good science movie. It's not a computer simulation of any kind, but it's a very sophisticated animation, which is surprisingly correct, accurate. And that's why I'm going to show you this. And this is a fantastic DVD narrated by Morgan Freeman. So if you had a copy somewhere, I do recommend you take a look at it. So the universe is born and expanding. And so now, this is the expansion. The universe is hot and dense. And as the universe expands, it cools down. But one thing that I want you to note, which will be crucially important for my talk, is that the universe is already lumpy when it was born. This is important because these are the seed for galaxies that we see. Now, the universe is quite opaque. Photons are constantly scattered by free electrons. The universe is fully ionized. Up until the universe cools down to 3,000 kelvins, the universe becomes transparent because the electrons are now captured by protons forming neutral hydrogen, and now the universe has become transparent to photons. This is about the time when the universe is 380,000 years old. The universe was 3,000 Kelvin temperature. The universe continues to cool down, but then you start seeing that these little lumps now start to merge. And this is indeed what we know from the standard cold dark matter scenario, where small things form first, they continuously merge to form bigger and bigger structures. And these little things, these are dwarf galaxies, and they continuously merge to form galaxies as big as our Milky Way. That's the standard picture. But then the question is, where do these ripples, fluctuations come from? And that's really the question about the origin of structures. That's the question about the origin of ourselves, because unless these ripples existed right after the birth of the universe, we wouldn't exist here. So this is the fundamental question regarding the origin of ourselves. Now, how was cosmic micro background created? And in order to understand, so physics of cosmic micro background is very, very simple. And there is this astrophysicist called Masataka Fukugita. If you laugh, then you know that he is a very peculiar character, excellent astrophysicist. He keeps telling me that cosmic micro background is a kindergarten physics. It's so simple that the kindergarten kids can even solve it. It is simple. It's not that simple, but it is simple indeed. So when it was hot, it was a hot soup made of protons, electrons, and helium nuclei, which would then constantly scatter photons. So photons and protons and electrons and helium nuclei, they move together. They behave as if it was a single perfect fluid, or almost perfect fluid. Neutrinos are there, they don't do much. Dark matter is there, they don't interact with photons, but they provide gravitational potential. So very, very useful analogy is that you can think about this as a soup, say, tomato soup. Then you have tomatoes, like protons and stuff, or maybe kartoffel, like helium nuclei. Then they are hot soup, very hot, like 3,000 kelvins. And you need to have a bowl, however. You need to have a bowl, to sustain the soup. And that's gravitational potential. That's dark matter. So dark matter doesn't interact with photons or electrons, but they provide gravitational potential. Now, this gravitational potential is time dependent. They change over time. As this ball, changes over time, what's inside also changes. So photons, blue shifted, red shifted, depending upon how these gravitational potential change over time. So remember that picture because that becomes very useful later. Then, universe is a hot soup made of these free electrons and protons and helium nuclei, and these photons are constantly scattered by electrons, so the universe is quite opaque. But when the universe cools down to 3000 kelvins, then electrons are captured by protons, they give nuclei to form neutral atoms. They do scatter photons, but not as much as Thomson scatterings by electrons. Therefore, these photons more or less propagate freely afterwards. So these are the photons we see now. In other words, when we observe cosmic microwave background photons, there are 400 of them per cubic centimeter now, an enormous amount of photons. We are taking the digital camera photograph, literally speaking, of the time, the universe at the time that the temperature is 3000 kelvins. So this is a snapshot that we can take, and this is indeed the photograph of the early universe. So cosmic microwave background is the farthest and oldest light that we can ever hope to observe directly, because before then the universe was opaque. But this is pretty early, so 380,000 years old. Current age of the universe is 13.7 billion years old. Therefore, this is equivalent of essentially the universe when it was born, well, just right after it was born. Then let me show you this more vividly. This is a striking animation created by NASA. So this is our Milky Way, and then we will put ourselves into the right location. So that's us, and then we put them 80 kiloparsecs away from the center. Then we are surrounded by sky 360 degrees, but then we wanted to put them on a piece of paper, so we expanded around. This is the galactic coordinates, and these are Magellan clouds, galactic center, of course. Then this is the optical image, and if you go to near infrared, so now wavelength is increasing. If you go to near infrared, you see starlights here, as well as this zodiacal light. It's a reflected light from the sun of the interplanetary dust. Usually nuisance for astronomers, but for people who study dust, this is a great resources. Move on. Then we go to far infrared. Then we go to submillimeter regime. We start seeing the emission from cold dust. Herschel, for example, observed a bunch of these. Then we go on, and we start seeing this brilliant cosmic microwave background, completely uniform, rather boring image of the sky, and it's much brighter than the galaxy itself. So cosmic microwave background is in fact the most dominant light at that wavelength. However, if we can then improve the sensitivity of our detector by factor of 100,000, we can start seeing ripples like this. And these are the ripples that existed right after the beginning of the universe. We know that these photons came from the time when temperature of the universe was 3,000 kelvins, right after the beginning of the universe. So where did they come from? That's the question. So this was detected by COBE satellite in 1992. They got the Nobel Prize for this. A successor of the COBE is the WMAP satellite. So this will be the machine that I'm going to be mostly talking about. So the WMAP, Wilkinson Microwave Anisotropy Probe, is a space satellite. Of course it's a space satellite. It's a space telescope. But it's not the optical space telescope or submillimeter space telescope, it's a microwave space telescope. So it's got the parabolas. It doesn't have just one parabola, it actually has two parabolas, because what we are interested in measuring is the fluctuations, anisotropy, the variations of the temperature across the sky, on top of 2.7 Kelvin background C. But we're interested in measuring 30 microkelvin fluctuations on top of 2.7 Kelvin. So how do you do that? You're staring at the one position of the sky and trying to subtract 2.7 out of 2.70001 or something. It just doesn't work. So instead of doing that, COBE decided to do the differential measurements. Namely, you take the photon from one direction, you take a photon from another direction, and they only take the difference. and we observe the difference. In this way, the measurements become quite stable. You get rid of these 2.7 Kelvin uniform things by looking at the difference between the intensity of a photon coming from two different directions. So this was a very clever idea put forward by Kobe. It worked brilliantly, so we decided to adopt this for WMAP as well. Another thing that made WMAP quite successful was the fact that it doesn't have any cryogenic cooling. It only cools due to the radiative cooling in Lagrange 2 point, down to 90 kelvins. This means that you don't have to worry about, say, noise coming from coolers or running out of helium or some unexpected accidents in space, because you can't fix it. So in this way, the lifetime of WMAP becomes almost indefinite, because you don't have to worry about running out of coolers. You could do a more sensitive experiment like Planck, but WMAP didn't choose to do that, therefore it was launched much more quickly than Planck. I will mention a little bit of Planck later. So this was a Kobe, made a map like this. This is a WMAP, made a map like that. So Kobe didn't have a parabola antenna, he only had a horn antenna, which is tiny. Therefore the angular resolution was much worse than WMAP. WMAP has a rear mirror, which can better focus the light. Therefore angular resolution is 35 times better than Kobe. And the WMAP is the first satellite, the scientific satellite that went up to Lagrange 2 point. And this is the 1.6 million kilometers from the sun. And it's an excellent site because you can get sun, earth, and moon behind your solar panel. So you don't have to observe microwave emission from sun or earth or moon. And you're always looking at the opposite direction. And also, you can constantly get powered by sunlight. So that's really excellent. And WMAP was launched in 2001, then continuously observed for 9 years. And then 2009, Planck satellite was launched. It's a successor of the WMAP, European mission. And it reached L2 as well. So now Lagrange 2 point is a little crowded, a little more crowded. And Herschel is also there. In fact, Herschel and Planck were launched together. And then we heard a rumor that Planck was doing just fine. So we said, okay, that's it for us. So after 9 years, we asked WMAP to happily retire. So WMAP moved to different orbit, heliocentric orbit, 1.07 AU from the sun. It's orbiting around there. And then finally we released the papers and 9-year data sets 2 years ago. Huh? Yeah, a year. It's only a year. This is the science team. It's about 20 people. And the last set of papers we got out were these papers, a couple of papers. And so let me show you the data. So this is the, so WMAP has 5 frequencies, 20 gigahertz to 90 gigahertz. And this is the full sky map, so this is galactic center again. And you see emission from galaxy everywhere. This is mostly synchrotron radiation. Then you go to the higher frequencies, the synchrotron goes down. If you go to 60 gigahertz, it's really the minimum of the foreground. Then if you go to 90 gigahertz, the emission goes up. Here, for example, in this region. This is because you have switched from the synchrotron, free, to thermal dust emission. Now we have 5 components, as far as we know, in the sky. Cosmic macro background, whose temperature doesn't depend on frequency because of black body spectrum. Synchrotron, whose antenna temperature goes down like 1 over frequency cubed. Free emission, whose antenna temperature goes up 1 over frequency square. Thermal dust emission goes up, frequency square. Then there's something called spinning gas, rapidly rotating tiny dust grains aligned with magnetic fields. Their spectrum is more complicated. But the bottom line here is that we have 5 components, we have 5 frequencies. You can do linear algebra and get rid of galaxies. So that's the cosmic micro background map. Then question is, once we're given the map like this, how do we analyze them? So first thing we wanted to see is whether these fluctuations we see are noise or signal. So in order to see that, we can just simply do something called the two-point correlation function analysis. So let's say you take 2 points on the sky, measure temperatures, in this case cold and cold here, multiply them together. In this case, if you multiply them together, you get positive. Negative times negative is positive. You then repeat this for a fixed angle over this ring. Then if your answer is like this, right? So cold, 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 cold. And if you average them all together, you still get net positive. This would be a positive correlation. So it's not random. You can do the same thing here and there. So it's positive, positive, product is positive. And you do this over the angle. Then if it's still positive, it's positive correlation. You can also have the situation where you have a negative and positive. Then you do this. And if the result is that the product is always negative, it means there's an anti-correlation, which is still a correlation, it's not the zero correlation. Now you do this over the sky, then you find that the average becomes zero. It's neither positive nor negative. Then it's a no correlation. So that's noise. Okay? So we want to see that, whether the data are consistent with noise or a signal is there. For some reasons that becomes apparent later, so this is a good statistics, but we normally do this not in real space, in theta space, but in the power spectrum space, the Fourier space. Because we're dealing with a sphere, we don't really do Fourier transform, which requires a box, the three-dimensional box, or two-dimensional flat space. We do Legendre transform. But it's only the detail that you don't really have to worry about. The only thing you need to know is that this power spectrum measures the amplitude of fluctuations that exist at a particular scale, angular scale. And this L, just like Fourier transform wave number, is related to 1 over length. And in this case, relation is L is equal to 180 degrees divided by theta. For example, this is what Kobe saw. This is why the Kobe team got the Nobel Prize. So this is the amplitude of fluctuations. It's temperature squared, so it's microcalorie square unit, versus angular wave number. And you see that there are all these measurements which are not zero. So many sigma detection of anisotropy in the sky. So it's not noise. Something is there. This L of 2 is called quadrupole because 180 degrees divided by 2 is 90, and this essentially divides the sky into 4. So hot, cold, quadrupole. And the Kobe, because it had a tiny phone antenna, it couldn't really measure anything beyond 10 degrees. So the data points cut off at the level of about 20. Now with the WMAP, we can do much better job. Because WMAP's angular resolution is 35 times better. Then this is what we saw. So this is Kobe. Then WMAP is like this. So this is really amazing. If you look at map like this, you don't really think that something that looks like an oscillation is hidden there. It's quite remarkable. So what's the physics behind this? And physics behind this is kindergarten physics, okay? So it's just a sound wave. I forgot to change miso soup to kartoffel. So you have some favorite soup, you can think of you throwing kartoffel or whatever, and then you start creating sound waves. Sound waves propagating everywhere. That's why you see it. In fact, it's not even analogy. If you look at the equation, they're identical. You have this system composed of proton, electron, helium, nuclei, and photons. They move together, and when you try to derive the density fluctuations in that fluid, obeys the wave equation. That's all. That's all we have here. And these waves don't actually propagate forever. They actually dissipate. So that's why you have this damping oscillations here. But then dumps. That's all. It's indeed kindergarten physics. The important thing is, just like you, for example, hit the, so if you don't like the soup analogy, you can think about metal. So like a flower vessel. The flower vessel made of ceramic, flower vessel made of copper. So you hit the vessel, listen to the sound it creates, and your brain actually knows that if you hit the copper, it creates a high frequency sound. When you hit the ceramic, it creates low frequency sound. And by listening to that sound, your brain automatically tells you that this flower vessel is made of copper or ceramic. We do exactly the same thing here. When universe is made of baryons, proton behaving nuclei, a little bit more or less, it changes the waveform. Likewise, when you change the amount of dark matter, it changes the waveform. And that's how we determine the baryon density and total matter density. In fact, details aside, first peak to second peak ratio, it tells you baryon density. So amount of protons and helium nuclei. This will tell you whatever the matter that interacts with photons. Now, first peak to third peak ratio tells you the amount of total gravitational potential. So, in other words, whatever that makes gravitational potential can be seen from here. And the amount of gravitational potential you get from this, an amount of matter that interacts with photon you get from that, don't agree. So that's the definitive evidence that the dark matter exists. In other words, with CME, no matter is left behind. We can measure the amount of stuff that interacts with photons and amount of stuff that doesn't. So we can measure everything, like with this. And at the time that when the universe was 3,000 kelvins. Now today, universe is 3 kelvins. So universe has expanded by a factor of 1,000. You know that if universe expanded by a factor of 1,000, the matter density dilutes by a factor of 1,000 cubed. So we now have billion times less dense matter. But that's something we know. Now then, we can compare the matter density we get from cosmic micro background to the total density that we measure and see whether they agree. How do we do that? We do the following way. So, cosmic micro background photons propagated for many, many years to come to W. Therefore, what we observe is something in angle. But we actually, given the baryon density we measure from the cosmic micro background, we can actually calculate what the physical wavelength of the cosmic micro background is. It's more like 150 megaparsec. So we can calculate the physical scale that corresponds to this first peak, for example. And we subtend the angle in 1 degree, from which you can calculate the distance between WMAP and cosmic micro background lasso scattering surface. By the way, by simply dividing that quantity by speed of light, you get the age of the universe. That's how we get the age of the universe. We don't measure age, we actually calculate age from distance. And that's why we can get very, very precise determination of the age. We never measure age, we actually measure distance. That's number one. Number two, this distance is determined by all the energy density in the universe, including something that does not matter, if such a thing exists. More precisely, the angular distance, this distance that we measure from the angle, depends upon 1 over energy density of the universe integrated over time. So in this way, we can actually get the handle on the total energy density today. Then we compare total energy density that we get from this distance and the matter density we infer from cosmic microwave background. They don't agree. So we have this total matter density that's about 30%. What's left is some form of energy that we don't know. Like that. So let me tell you why we think this is not matter but dark energy. Reason is simple. Like I said, no matter is left behind. We know all the amount of all the matter in the universe. We have a complete account of matter density in the universe from cosmic microwave background. They have some way of measuring total energy density of the universe today. You compare them, they don't match. That's all. So that's how we know that this component isn't matter. So you probably, of course, heard about dark energy. We have our experts in Heidelberg. But for fun, because of course we don't know what the dark energy is. So we have hard time thinking about it or imagining it. But this movie turns out to be quite useful for you to realize how you actually think about that. Okay, so let's go. So this lady, actress in Japan, is asked to throw an apple to a bug. And in the world without dark energy, of course, apple just falls back down. Now, of course, just in case you wonder, we don't experience dark energy on Earth because the baryons, concentrated, and baryon density or dark matter density also around us much higher than the dark energy density. Just around the solar neighborhood within the Milky Way. If we go to the outer space, intergalactic medium, where the matter density is much lower, then the dark energy density becomes dominant. But of course, on Earth, baryon density is much more dominant. But nevertheless, let's imagine that we actually have a situation where Earth is dark energy dominated. And you would experience something like this. So, like that, right? And that's remarkable. It's ridiculous, but that's of course what's going on in the universe, right? Now that I want you to sort of reflect upon this. How many of you think that thought that this was okay? So two questions, right? Or one question. So two choices. So by looking at this, you thought that you felt that there's some force between the apple and the girl. That's one choice. Another choice would be something happened to the space between apple and girl. Right? And if you thought that you felt like there's some force between apple and a girl, which was pushing apple to the bottom, that's a modification to the Einstein's general relativity. It's a modified gravity solution to that energy problem. If you thought that something happened to the space between apple and the girl, namely somehow space started to expand like crazy. It's a property of space rather than force. Then that's the dark energy hypothesis. Namely, dark energy modifies essentially with the dark energy, the space expands much faster. So, whether it's a modification to gravity or the property of space, something we don't know. And that's what we're trying to figure out in the future using something like, for example, galaxy survey, something like Euclid. Okay, so what about, however, the early universe? So that's the main topic of the talk. Back to the cosmic soup, right? And you saw that sound waves are created only when, say, tomato or kartoffel were dropped. But who dropped those things? That's the question. Unless somebody dropped those stones or kartoffel or whatever sound waves won't be created. So the fact that we see these sound waves must mean that there was an original fluctuation coming from somewhere else, from the beginning. So here comes then the idea, the crazy idea called the inflationary idea, proposed back in 1980s. It tells you that universe accelerated and expanded by enormous factors, something like 10 to the 26 times or more, within a very short time period, like 10 to the minus 36 seconds. In other words, within a tiny, tiny fraction of a second, the size of an atomic nucleus becomes the size of a solar system. That's what the inflation is. And if you think that this is a reasonable idea, you really have to rethink. Especially, if there are graduate students who work on inflation and never doubted that inflation was right or wrong, you should really rethink about that. Because this, if you believe this at once, you probably should quit the physics because you don't have a right taste for the standard physical processes. This is ridiculous, okay? But that's why this is also fascinating that now we can test this hypothesis observation. Unless this is tested, you should never believe this. But now we can actually test this observation. That's exciting. And so cosmic inflation, the dark energy makes the universe accelerate today. So universe becomes double, size doubles within 10 to the 10 years, 10 billion years. Here, size of the universe becomes bigger by 26 orders of magnitude within 10 to the minus 36 seconds. Okay? So that's how ridiculous that is. If you think dark energy is ridiculous, going up, this is much, much, much crazier. Now, how do we go about this? So let's do the following exercise. So we know that these ripples, these sound waves are created by the fluid. So baryon photon fluid reacting to these perturbations from coming from there. Now, but we now measure from the peak wave fields, we now measure the amount of dark matter, amount of baryons. So we can now undo the oscillations. You'll get something like this. So almost equal amplitude of fluctuations over all angular scales. This is called scale invariant spectrum. In other words, whoever dropped the stones, they decided to drop the stone so that fluctuation at all scales, big waves, small waves, they all receive the same amount of perturbation, initial perturbations. It's a democratic perturbation. It doesn't care about the scales, right? But the whoever dropped the stone didn't have to do that, okay? So this is one possibility. Another possibility is that you have more power on large scales than small scales. Or more power on small scales on large scales. You can do that. So let's parameterize this by the following form. So the amplitude of fluctuations is proportional to angular wave number to some power, ns minus 1. If ns is exactly 1, then it becomes precisely scale invariant spectrum. If you have more power on small scales, then ns is greater than 1. If you have more power on larger scales, ns is less than 1. And inflation predicts that ns is roughly 1. So already, at this point, in fact, the data do suggest that the ns is roughly 1. So this already is it's rather indirect perhaps, but it's a very strong indication because this prediction was made in the 1980s, right? And after 20 years or 30 years or so, we now see it, okay? But there's more than that. So there's a remarkable story beyond this. So what determines this ns? You may ask. This ns is determined by expansion history during inflation. So what happens is the following. During inflation, the universe was small, so small that quantum fluctuations cannot be ignored. Now you have this quantum fluctuation generated on microscopic scales, of course, right? Microscopic scales. But now inflation happens, this crazy expansion happens, they stretch the region of these fluctuating regions to microscopic scales. So you thought that you were talking about, say, 10 to the minus 15 meters physics fluctuating, But within a tiny fraction of a second, that region that we're fluctuating becomes the size of the solar system. And bigger and bigger and bigger as the universe expands more. Then the amplitude of fluctuation that you create depends upon expansion rate of the universe at that time. Now I'll come back to that later. So stretching to micro to macro. So you create fluctuations of certain wavelengths on very, very small scales. But then inflation stretches the wavelength and this fluctuation becomes macroscopic. From the fluctuations, so the Heidelberg uncertainty principle, right? So you can borrow a lot of energy from vacuum if you promise to return it to the vacuum immediately. Namely, the amount of energy you can borrow is inversely proportional to the time. And time is short, it's 10 to the minus 36 seconds. So the amount of energy you can borrow is gigantic. It's 10 to the 12 G. So these quantum fluctuations work like this. You have the fluctuation in energy that's proportional to the expansion rate during inflation. Right? Now something like this happens. Inflation began, quantum fluctuations are being stretched. Now, and inflation continues, and fluctuations are continuously producing stretch. Now let's imagine that you had a perturbation, fluctuations, produced initially, right after inflation, let's say. They are stretched. Then next fluctuation is produced. But this largest, the earlier fluctuations are stretched, continuously stretched. Right? So in other words, earlier the fluctuations are produced, the bigger the length scale that become. So large angular scale fluctuations were produced earlier in inflation. Smaller scale fluctuations are produced later in inflation. Now, if the expansion rate of the universe was constant during inflation, then amount of fluctuations you see at all angular scales will be completely equal. Because earlier fluctuations, later fluctuations, they all produce with equal amplitude. If the expansion rate of the universe is decreasing with time, then you see that the large angular scale fluctuations are bigger than smaller scale fluctuations. So in this way, you really measure how expansion rate of the universe changes over time during inflation. Because inflation has to end, this expansion rate goes down. Okay? Because otherwise, inflation will never end, and we don't exist. Clearly, you have to heat up the universe. So during inflation, the universe rapidly cools down. So crazy amount of expansion. You have to heat it up again, so inflation has to end somewhere. Therefore, usually, okay, inflation predicts that NS is close to 1, but slightly less than 1. It's not always the case. You can cook up the models where NS is greater than 1 from inflation, but usually NS is less than 1, with a deviation of order 10 to the minus 2. That's what the cosmologists are after for 30 years. WMAP's 9-year data. Yes, NS is close to 1 and less than 1, but significance was too sigma. Okay, who cares? What a pity, huh? But we can perhaps combine, because we are trying to measure the power index. If you had a bigger lever, if you cover the larger range in wave numbers, you can determine the index better. So perhaps we can do that. So then to do that, WMAP's mirror was 1.5 meter. So it cannot go much beyond this scale, 0.2 degrees. But you can build a bigger telescope on the ground. So you can build a 6-meter telescope in Chile, or 10-meter telescope in South Pole. Then that has a much, much better angular resolution. And we can map the fluctuation down to small angular scales. It's a beautiful measurement. It's amazing that we can achieve something like this. Then you can determine the NS. And it's less than 1 by 3.56. Okay, that's good enough for cosmologists. But perhaps not good enough for particle physicists. then Planck came out, right? So Planck is the ESA mission proposed in 1995, and then finally launched in 2009 together with Herschel. They did something amazing. So they launched them together, separate them in orbit, and then send them to the Institute. It worked. It's great. I'm not about the Planck, but this is a really wonderful measurement. And then finally, for the first time in human being history, and there's someone with more than 5 sigma from cosmic micro background data alone. Okay? So prior to Planck, we also combined WMAP with this Chile telescope and Southpole telescope, and also some pieces of other information coming from galaxy surveys, something that's not cosmic micro background. Then we could actually get an SSL1 more than 5 sigma. But that measurement, which we're very proud of, is not just CME. And if you wanted to prove something crazy like inflation, you don't want to just keep adding more assumptions. Right? If you want to combine CME with a galaxy, you have to make an additional assumption. But you don't want to do that. You rather want to have a single experiment rather than combining the WMAP and Chile and South Pole. You want to have the single experiment that covers the entire wave numbers and then measure everything by itself. And indeed, single measurement from Planck satellite, now nailed status, and that's less than 1. This doesn't prove inflation, but it gives you a very strong evidence for it. Now, how do we go beyond this? Okay, so this is wonderful. To me, this is as important as, well, perhaps not just to me, but to cosmologists. This measurement is perhaps, as important as the discovery of the Higgs particle. Perhaps not just yet, but this really provides a strong evidence for inflation, but not to prove. To prove this, you have to look at other things that inflation will create. So inflation, quantum fluctuations, produce fluctuations in space-time. Okay? That's what it is. Fluctuations in space-time can take 2 forms. One is so-called scalar perturbation. That's simply density perturbation, density fluctuations, sound waves. Another is a tensor fluctuations, which manifest themselves as gravitational waves. And inflation produces, so you now see that this scalar fluctuation, temperature and isotropy over gigaparsec length scale, right? So inflation stretches microscopic things to gigaparsec scales. Inflation produces the gravitational waves whose wavelength is gigaparsec. I don't know any other wave producing such a ridiculous thing in the universe, right? So if you see a gravitational wave whose wavelength is gigaparsec, that's the proof of inflation. So how do we do this? Gravitational waves are coming toward you. So what do? You have the particles in front of you in the form of a ring. And what gravitational waves do is to change the distance between particles, like this. And so space is being stretched or contracted continuously. And this is wonderful because you put the electron here, right? And from the point of view of electron, this part of the space is just being stretched. So then, wavelength of photon is also stretched. So the photon coming from this direction is redshifted. Photon coming from that direction is blue shifted. So this automatically generates temperature and isotropy. Today, this gigaparsec gravitational wave is with us. And it stretches space in quadrupolar way. And if you look up here, gravitational wave stretches things upwards, so photon will receive from that direction is called boson. We can measure that. But we haven't detected anything yet. So you can parameterize then this power in gravitational waves to power in gravitational potential. So that ratio is called tensor to scalar ratio, so essentially gravitational waves to gravitational potential wave. Inflation predicts that this quantity is small but non-zero. We haven't seen anything yet. So we can now have this diagram where y-axis we plot tensor to scalar ratio. X-axis we plot this ns. Then if you combine all the data that we had before Planck, so WMAP, CM experiments, and some galaxy surveys data here, we have this contour here. And S is less than 1, and R is less than 0.1. No detection yet, so the contour doesn't close here. And there are a bunch of points here. These are inflation models. This is a model prediction based upon the physics right after the birth of the universe, where energy density of the universe was equal to the grand unification energy scale. Something that is something like 10 to the 13 times. Hold on. 10 to the 13 times higher energy than we could achieve in LHC. So cosmology is the only way really that tells us the physics of that scale, and we're doing experimental physics or astrophysics, ruling out models of grand unification energy scales. So that's why we're doing this. Very exciting. Then that's how we can really do the precision science regarding the high energy. Now, Planck was launched and did a fantastic job, and Planck got this result here. Okay, so they are essentially identical. But like I said, Planck could do this by CME data alone. So the importance of that cannot be overemphasized. Here we had to combine with this large-scale structure data. If we didn't, we have this weaker constraint. But with Planck, now we firmly have this exclusion plot. So I have maybe 2 more minutes. So how does inflation happen? If anyone asks you that question, your answer must be always be we don't know yet. Okay? You're free to say, I like inflation, I believe inflation has happened. You cannot say it has happened. Okay? We don't know yet. So we have to detect gravitational wave from inflation. How? It's a cosmic micro-background polarization. Now, actually, I don't have time to tell you how it works. But let me just now say that cosmic micro-background is polarized. Okay? And let me just, these are the current data that don't really tell us much about the gravitational waves. But let me just tell you quickly how cosmic micro-background is polarized. There are only 2 things that you have to know. It's not cosmological. It's electromagnetism. You need to have a Thomson scattering, and you need to have an isotropic radiation field around an electron. That's all. So that's how it works. You have this incoming light from the left, then there's an electron here that scatters. Because the electric field goes like this from the incident light from the left, electron gets oscillating this and produces light from that to that direction. Right? So that's a scattering. However, the light that's oscillating in this direction cannot produce light to that direction because light is a transverse wave. You cannot produce oscillations along the direction of the photon. So that's just a classical way of thinking about Thomson scattering. Of course, there's a quantum way as well. Okay, so this tells you that the single scattering produces polarization. Yeah? So you see the light scattered off the surface of the ocean, or you see the light scattered off the windshield of the car. They're all polarized by this mechanism. But that's true only when you have one direction of the incident photon. If you have multiple directions of the incident photons, then just having scattering is not enough, because if you have light from the above with equal intensity, then the light from the above gets scattered and produces the exact same amount of radiation in the opposite direction, orthogonal direction of polarization. So net result, that there's no polarization. Now finally, if you have a situation where an electron is surrounded by quadrupolar temperature anisotropy, hot, cold, then finally you get that, okay, hot photons coming from the left, cold photon coming from the above, then what's synthesized afterwards, there's a symmetry between horizontal direction and vertical direction. There you go, you have a net polarization. And what's important here is that polarization direction, which is now here, okay, is parallel to hot regions. So it becomes important later. So, okay. Now, now coming back to gravitational waves. Okay. Gravitational waves produces quadrupolar temperature anisotropy. Like that. And this is wonderful because right there already you see electron is automatically surrounded by quadrupolar temperature anisotropy that you need to produce polarization. And polarization direction is parallel to the hot region. So polarization direction will look like this. This is what we want to measure. Now, this is the polarization direction produced by gravitational waves. But there's another way to produce polarization. Namely, if you have a gravitational potential, stuff is falling in, that also creates quadrupolar temperature anisotropy and then gives you polarization. However, there's a distinction. There are two modes of polarization. One is called E mode and another called B mode. And if there's a gravitational potential here, and stuff is falling in, it actually produces radial polarization like this. So this can be produced by gravitational potential. You don't need gravitational waves to produce this. Gravitational waves, however, can produce this kind of mode as well. Why? So first of all, gravitational potential, which doesn't really have preferred direction, only produces symmetric pattern like this. But gravitational radiation, okay? When one horizontal polarization like this is produced, there must be accompanied 45-degree tilted polarization. Because gravitational waves have these two distinct modes of oscillations. When you have one oscillation mode like this, you must have another with equal amplitude. So when you see one polarization mode that looks like this, there must be corresponding 45-degree tilted polarization as well. You must see both with equal amplitude. So if we see this E mode polarization pattern here, so-called, we must also have the equal amplitude of this B mode. That's the smoking gun, because this B mode cannot be produced by gravitational potential. It's only produced by gravitational waves. So this is the power spectrum of the E mode power spectrum, and this has been measured, you see. This E mode polarization has been measured with very, very precise accuracy. This is due to gravitational potential, not gravitational waves. And this line here is a prediction from temperature anisotropy and goes through the data points. So it's a triumph for standard cosmological model. But there's no B mode here. B mode hasn't been observed yet. So the next step is that, so I'm Japanese and we're working with the Japanese colleagues to build a next generation cosmic micro background satellite, so after Planck. This will be dedicated to polarization measurements. We're going to do the polarization measurements 10 times better than Planck. And the target is that this R is going to be 10 to the minus 3. So we can detect this R if it's 10 to the minus 3, which is 2 orders of magnitude better, smaller than the current limit. And if the inflation happened, and then it's a great chance that we can see gravitational wave at that level. Target launch is 2020. It's not funded yet, but we think there's a good chance. Okay, so that's the last slide, summary. So WM has completed 9 years of observations. We could determine age, composition, expansion rate, etc. from cosmic micro backgrounds, hot soup, or sound waves. But what's really exciting at the moment is we could really even push the boundary farther back in time and start to talk about experimentally testing our idea of the beginning of the universe, namely inflation. And for the first time, NS less than 1 is now discovered with 105 signal. Strong evidence for inflation, but not the proof. in order to prove that inflation happened and put that in the textbook of the, I guess, kindergarten, then we claim that so to do that, we have to detect primordial gravitational waves in B-mode polarization. Then we claim a victory. So I'll stop here. Thank you very much.
So thank you very much. It was a very nice talk. And one thing I learned is that in Japan, the level of education is very high if they do this kind of stuff in kindergarten. So I'm very impressed. But I'm sure that there are numerous questions here. So as usual, let's start with the students and postdocs. So, yeah, please go.
Sorry, I didn't understand why inflation predicts n s to be less than 1. Could you please explain it again?
Yes.
Thank
so inflation continuously produces fluctuations. Okay? The strength of the fluctuation is proportional to the expansion rate of the inflation. So if expansion rate goes down with time, the strength of fluctuation goes down over time. And earlier fluctuations were seen on larger scales. Later time fluctuations are seen on small scales. And that's the reason.
Thank you.
So you said that you would, in a perfect case scenario, the power spectrum would be flat, or ns would be 1, right? So the deviation is sine of the decrease in exponential rate. But how do you, but that is assuming, as you said, quantum fluctuations.
Yes.
Were there before inflation? And my question is, how do we know, or how secure do we think to know the spectrum of those fluctuations before inflation set in?
Okay, so no. Yeah, actually, so these fluctuations were not laid out before inflation. These fluctuations were produced during inflation. In fact, great thing about inflation is that anything that happened before inflation would be totally diluted. Inflation is a great way to forget about everything that happened before. Really. But the inflation itself continuously produces fluctuations. And that's what we see. Yeah, so it's primordial in a sense, but we don't really look at the beginning of inflation. We really see what happened during inflation. But that's pretty primordial though, because that's really right after the beginning of the inflation.
So, what variety of non-inflationary theories would still be hiding in the current parameter space constraints, and what would be the smoking gun that would reveal such theories in terms of evidence?
Yes. So that's a great question. So is the inflation the only way to understand data? Answer is no. However, all these alternatives to inflation for producing fluctuations predict negligible amount of gravitational waves on gigaparsec scales. So if you see gigaparsec scale wavelength gravitational waves in the form of this B-mode polarization, for example, then inflation will be singular. So I think the community agrees now that if you see B-mode polarization, that's inflation. So that's why it's not the proof of inflation just yet. We really need to see gravitational waves.
So the amount of gravitational waves depends on the energy scale,
Right.
the expansion. What would be the lowest energy scale that we could reasonably hope to measure?
It's like 5 times 10 to the 15 GeV.
It's still pretty high.
It's pretty high, that's right, yeah.
To place the smaller energy scale, we would not be able to see.
That's right. That's right. Yeah, so in fact, that's a good point, of course. So, good side of the story is that if we see gravitational waves, we know inflation has happened. But if we don't see it, it just means that the energy scale of inflation was a little below the random unification scale. So we don't rule out inflation by not detecting gravitational waves. That's a dilemma, but there's nothing we can do about it. We just go ahead and just make an observation. If we see it, great. If we don't see it, then we think about something else. good. So with cosmic micro background photons, we can only see up to 380,000 years after the beginning of the universe. With gravitational waves, we can go far back, essentially inflation time. That's 10 to the minus 36 seconds after. With neutrinos, neutrinos are weakly interacting, more weakly than photons, but less weakly than gravitons. So with cosmic neutrino background, we can map out, we can go up to 1 second after the beginning of the universe. And that, of course, tells us a lot about primordial fluctuations as well. Now, the existence of this neutrino background has been already proved. So it has been already detected in the form of their influence on cosmic micro background. So we see cosmic neutrino effects through cosmic micro background. But of course, we're not satisfied with that. It would be nice to make a map of neutrino fluctuations using neutrinos. Now, we're detecting neutrinos, lots of them, Kamiokami, ice cube, so why can't we just do that? Okay, fine, so let's think about it, okay? Sun produces neutrinos. These are radioactive neutrinos with energy of about MeV. Now, the MeV neutrinos now kick nuclei in water, and we measure this recoil. The energy is small, but okay, we can still measure it, barely, but we can still measure it. Good. Okay, now this ice cube and so forth, okay, this gigantic cosmic events, explosion or acceleration particles, you produce GeV neutrinos, TeV neutrinos. Okay, those things are easier to measure because the recoil energy that they have on the nuclear will be large enough to be measured. Good. So it's maybe the question is not that the neutrinos are weakly interacting. It's fine. We have tons of water, and then they interact. So that's fine. What's challenging is the measuring this recoil energy. Right? Now, the cosmic micro background radiation is 2.7 Kelvin. Neutrino background is 1.9 Kelvin. And that's what is it? It's millielectron. Recoil energy, or say microelectron, right? So something like that is what we're talking about here. That's difficult. That's the challenge. But I know that, however, the particle experimentalists on their spare time do think about this. So maybe eventually we'll see.
Okay, let's open the discussion to everybody. Any further questions?
So some people say that the Planck data now poses some problems on the shape of the inflationary potential that are allowed, which makes it unnatural. And those people, for instance, propose instead that periodic models would be more natural given the Planck constraint. So what would those models have to say about the primordial gravitational waves?
So those models will say zero gravitational waves on large scales.
So that would be a great news.
Yes.
If we see that as a rule out.
Yes, that's right. Yes.
Further questions?
You found with WMAP also the anisotropies of the fluctuations, and initially it was questioned whether this was an instrumental effect or not. And our Planck has confirmed this. And I wonder what your interpretation of that really is.
Yes.
I mean, it's mostly due to the inflationary phase, but what do you do to account for that?
Yes, so my answer will be quite boring. But first of all, let me just show what the question is. So we have this cosmic micro background map here. And then some people claim that if you divide the sky in this direction, then there is more fluctuation in the southern hemisphere than the northern hemisphere. Okay? Good. So that's a large scale asymmetry of the power. So when we say asymmetry, what we really mean is that the variance of the temperature anisotropy here is smaller than the variance of the temperature anisotropy you see here. In this statistically isotopic processes, the variance of the anisotropy should be constant over all sky. But some people claim that that's not the case. So the claim was, in WMAP data, above, say, a few degrees, this asymmetry is seen. Okay? Then the Planck team said this asymmetry persists to small and small and small scales. Okay? So, okay, good. But so that was very, very strange. Okay? So people took that very seriously. Then later on, including ourselves, we visited this using Planck data and found that that wasn't really the case. So Planck team now retracted that thing, and the asymmetry doesn't exist on small scales, but perhaps on large scales it's still there. Okay, good. So both Planck and WMAP see this asymmetry on large scales according to some claims. Okay, what is the claim? Claim is about 3 sigma significance, there's this asymmetry. Okay? Fine. Okay? So for us, for me, for example, 3 sigma, who cares? I've seen enough 3 sigma in my life that I just don't take that seriously. Second of all, okay, now I spoke about this scale dependence, okay? Large scale versus small scale. You then try to calculate what the significance of the asymmetry as a function of angular scales. You change the angular scale, significance goes up and down. If you choose then right angular scale, it goes up to 3 sigma. But your angular scale is a little bit below, a little bit large, significance drops to 1 sigma. This is something called a posterior choice of the angular scale, or more fancy name after Selm is a look elsewhere effect. If you take that into account, significance is now not even 3 sigma, it's actually 10% chance that you can find this in the data. So WMAP team stated this clearly in the 7-year release that this is a statistical fluke. So the bottom line message is, it's anyway 3 sigma, even if you ignore look elsewhere effect, who cares? And second of all, if you do take into account look elsewhere effect, it's a 10% effect. So it's just not there. So that's not.
Okay, so with this reassuring remark, I would say let's thank Eiichiro again.